Okay, good afternoon, everyone. So today we're going to learn some more math. Before I do that, though, I've been sent an email by the people who do the contact tracing for the COVID pandemic at our university. They mentioned that there's been recorded positive cases of COVID spreading in our classroom. So if you feel like you might be sick, or if you feel like you're concerned about getting sick, you're recommended to go get a test sometime between now and like the next 5 days or something like that. So they just send out those emails anytime that somebody in a classroom gets COVID and has a recorded case. So we've had at least one in our class. So I've been told to let you all know that just for your own safety. Any questions about that? Okay. I know everyone and their brother kind of has COVID right now, so just be careful out there. Get tested, and try not to spread it to other people if you can. All right. So we're going to do sections 1.3 and 1.4 today. I'm now 2 days behind the schedule. I'm going to try to speed up a little bit today. The homework is going to be due on January 25th. So after today, you should be able to do questions 1 through 12 on the first homework. I'm going to have office hours today, as always. Okay, so every day after class, from 3 to 4:30, you can get on Microsoft Teams and meet with me and talk about anything. I really recommend that you follow up on, like, if you're confused about something we do in lecture on a given day, just follow up in office hours that day, and it will help you a lot. So do that. The SI sessions are up and running. Daria, you have anything to say about that?
Yeah, tonight I'm gonna have one from 6 to 6:50, close heap 350. So it's like the first room on the third floor, you'll find that.
Okay, so if you want to do your homeworks in a collaborative environment, okay, going to the SI sessions or coming to office hours is a great way to do that. Okay, so Daria and I are not going to give you the answers to your homework questions, but we are going to help you find those answers on your own. Okay, so if you want that help, it's free. You don't need to hire anyone, you just have to show up. And yeah, okay, so that's homework and office hours and SI sessions. Do you have a question?
No. Sorry.
Any administrative remarks or questions? All right, then let's get started for today. Oops, I'm too far ahead, I think. I wanted to do one more thing from 1.2, which I think is useful. So let's warm up on our own, okay? So individually, take a couple of minutes to try out this problem number 6, which is from section 1.2. Okay, so we're asked to fill in this table with some check marks for how many intersections we think two lines are going to have if they have the same slope, different y-intercept, same slope, same y-intercept, different slope, different y-intercept, or different slope and same y-intercept. Okay, so we want to know how many times two lines are going to intersect. Now we know if we have two lines, they might not cross, or they might cross once, or they might cross each other infinitely many times. I'll leave it up to your imagination to think about how that could possibly happen. So let's just take a minute or two to fill out this table here on our own, and we'll discuss. All right, would anybody like a little more time to finish up? Okay, a little more time. Take another 30 seconds or so. Alrighty, let's go ahead and discuss these. Okay, so we have all different types of the ways that two lines can interact with one another. Okay, so I'm going to try to color code this. The first one I'll do with blue, and I'm going to draw a picture of each situation to help us figure out what's happening here. Okay, so if we have two lines which have the same slope, there's a special word we use to describe two lines that have the same slope. Does anybody know what it is? It starts with a P. Parallel, very good. Okay, so if we have parallel lines, that means they go in the same direction. Okay, so they go in the same direction, but they have a different y-intercept. Okay, so one y-intercept could be here, and one y-intercept could be here. So we'd have lines which are going in the same direction, but passing through slightly different y-intercepts. Okay, so how many times do we think these lines are going to cross one another? Yeah, 0 times, right? They just go along side by side and never touch. Okay, then we'll do pink this time. We got the same slope again, but this time our y-intercept is the same for both of them. So here's line number 1, right? And then line number 2 has the exact same slope and the exact same y-intercept, right? So it looks like this. So what do we think for intersections? Yeah, infinitely many intersections. By intersections, it's a little bit of a weird word to use for two lines which are really the same line, saying that they intersect everywhere. Really what it means is just they overlap, I guess might be a better word for it, right? So that goes there. Okay, then we've got two lines which are different slope, different y-intercept. Okay, so one has a y-intercept here, one has a y-intercept here, and they have different slopes. Well, I think it's pretty clear. How many times are these ones going to cross? Yeah, 1 time. All right, and then finally for different slope, different y, or same y-intercept. Okay, we got the same y-intercept but different slopes. It just means that they cross each other 1 time, and it happens to happen, or happens to occur, at the vertical intercept. Okay, so I think that's, again, 1. Alright, so if two lines are literally the same, then all of their points are shared. If two lines are different y-intercept but parallel, then they never cross. But in the other circumstances, we're going to have lines which are crossing exactly 1 time, right? Okay, makes sense. Any questions about that? All right, let's move on to section 1.3. As I go, I'm going to scroll here and talk about a couple things. Okay, point slope equation for a line, we already discussed. General slope intercept equation for a line, we already discussed. These things which I put in this black box would be good practice for you, especially if it's been a while since you did a math class, okay? So I'd recommend that you practice those. And then as well, problem 8 and problem 9. Okay, good ones to practice, especially problem 9. This is a good one. All right, and then there's additional problems. So don't forget the quizzes, the problems for the quiz, one of them will come directly from the additional problems sections, okay? So the next quiz might come from here, or the additional problems from the next few sessions, okay? So if you practice all these problems from the additional problems, okay, you'll know how to do at least one of the problems on the quiz every time. Okay. So we're going to move on to a new section now, and this new section is basically going to start moving us in the direction of understanding the ways that functions change. Okay, so in calculus, this is really what we're interested in understanding. Okay, when we talk about derivatives later on, what we're going to talk about is how is a function changing at a given location. Okay, and then later on when we talk about integration, we're going to talk about, well, what happens to a quantity which accumulates change, right? Say I grow 3 inches every year, something like that. How tall am I going to be? How much height am I going to gain over the course of 5 years? These sorts of things deal with integration. Okay, so before we can talk about how functions change at a given location, we have to start with what we already know, which is how to understand the way that a function changes if it's a line, right? The way that the function changes as a line is described by that line's slope, right? How steep is it rising? How quickly is it rising? How quickly is it falling? Is it going flat, right? The slope of the line tells us the rate of change of a linear function. But if we don't have a linear function, it gets a little bit more complicated. But what we can say is, what is the average rate of change of that function by approximating that rate of change with the rate of change of a line? Okay, so that's a lot of words. What do I mean? The average rate of change of f of x on the interval from a to b. Okay, we should probably kern that a little better. There we go. Of f of x on a comma b is given by, I usually abbreviate AROC, average rate of change, is equal to f of b minus f of a, all divided by b minus a. And you might think that looks kind of similar to the slope formula, right? y2 minus y1 over x2 minus x1. Okay, that's because it actually is a slope of a line, and I'll draw for you which line it is. So first of all, another way we can write this is delta y over delta x, okay, if you want. And what does it really look like? Well, if we take a function which looks like, I don't know, what does it look like? Let's do one like this. Okay, we take a function which looks like this. Okay, and we let the a be an x value which is on the left, and the b is an x value which is on the right. Okay, then this point which is up here is going to be the point b comma f of b, right? We get the height of the function by plugging in the x value into the function. And same with a comma f of a, right? Then this average rate of change is going to be the slope of a line. It's the slope of a line which passes through the points a comma f of a and b comma f of b, right? So this actually is going to give us, okay, come on. My iPad has gone non-responsive. The slope of this line. Sometimes I'll call it the slope of the direct path. Is what the average rate of change gives us. Okay, so you can think about it in the following way. You could think about this in terms of, like, if I was driving a car. Okay, so let's say that this is describing my distance from home. Okay, so first I'm far away from home, and then no, I shouldn't describe it this way. let me describe it in yeah, okay, maybe I will say distance from home. So if this is my distance from home, right? Initially I'm this far away from my home, and then I come closer to my home. Here I'm at home, I drive farther away, and then I'm back at home, and then I drive in the opposite direction, and then I drive away a little bit over there, right? So if you think about that, then you can think about, well, sometimes in the car you're driving in reverse, sometimes you're driving forwards, but in the end result, you end up taking roughly this path, okay? Or equivalently, you could take that path. So let's say, let me draw a better graph. Let's say I start at home and I go slowly for a while, and then I speed up, and then I slow down and I stop, right? That's my graph. Well, I could achieve the same result by driving at a constant speed the entire time, which goes like this, right? So this is describing my average velocity, right? So if my function is changing at a certain rates at some points and certain faster rates or slower rates at other points, then we can achieve the same result by following this direct path, whose slope is given by the average rate of change of our function. Okay, this will become more clear when we do some examples. Any questions so far? Okay, let's get to it then. We're going to do a couple practice here. So let's take our function g of x equals x cubed minus 2x squared. We have a graph of it shown below, and we're supposed to draw a line segment between the points on the function where x is equal to 0 and where x is equal to 3. Okay, so where x is equal to 0, the point which is on the function is the height 0, so this is 0, 0. And then at 3, I guess it looks like it's 9, so this is 3 comma 9. All right? So now what we're supposed to do is compute the average rate of change of f of x on the interval 0, 3. Well, all I'm going to do is use my formula, okay? The interval AB here is the interval 0, comma 3. So wherever I see a B in this formula, I'm going to put a 3. And wherever I see a A, I'm going to put a 0. Okay, so f of B minus f of A over B minus A is going to be equal to f of 3 minus f of 0 over 3 minus 0. And f of 3 is given by the height of the function when x is equal to 3. And that's 9 in this circumstance. So we get 9. And then for the bottom part, or for the f of 0, excuse me, f of 0 is going to be the height of the function when x is equal to 0. So that's this point right here. And it's the point 0, 0. So its height is 0. And we divide by 3 minus 0, and we get 3. Okay, so this is telling us that the slope of the line which passes between these two endpoints has slope 3. And you can see that fairly clearly, right? We go over 1, 2, 3, so our run is 3, and our rise is 3, 6, 9, right? So we get a rise of 9 and a run of 3, so the slope is 3. Any questions about that first example?
Wait, where did the 9 on the far right?
This one?
Yeah.
So this is just tracing back. So first it was f of b. We know that b is 3, right? So we put a 3 in here.
Yeah.
So if we want to know what f of 3 is, we need to use the graph. Okay, so the graph of a function says you take an x value, which is listed here. Okay, in our case, it's the x value 3. And then the height of the function is equal to what you get if you plug in 3 into the function. So this here is really the point 3 comma f of 3. Okay, this is how we get the height of a function, is we take numbers which are on the x-axis and we plug them into the function. I guess it's g in this circumstance. I should have used g. Oh well, I can fix that. There.
Okay, so why do you have f of 3 minus f of 0?
why do I have f of 3 minus f of 0? So I'm just using the formula here. So the way I find the average rate of change of a function on an interval is I use this formula, f of b minus f of a over b minus a, where b and a are just numbers, okay? And in our particular, whoa, what just happened? In our particular problem, they tell us that they want us to find the average rate of change on the interval from 0 to 3. So that's how we find out what a and b are. Okay, so this is our a, and this is our b. That make sense?
Yeah.
Okay, so everywhere I see a b in this formula, I'm going to put a 3. And everywhere I see an a, I'm going to put a 0. So that's how I got 3 and 0 here. And then I just needed to evaluate the top part by checking what is the height of the function when x is equal to 3 and what is the height of the function when x is equal to 0. That's how I got the numbers 9 and 0, and then I subtracted them and divided by 3.
Got it.
Yeah, another question?
Could you kind of just skip that step and go straight to like the final step?
Yeah, if you want, but make sure you do it right.
Yeah. What, okay.
So if I was grading this and you just put 3, I would be a little bit hesitant to give you full credit. But if you put 9 minus 0 over 3 minus 0, that would make me happy. Happy enough anyway. So yeah, no, you don't technically need to write all this stuff if you don't want. Any other questions? Yeah.
So with the f of b and the f of a, would those be the independent variables?
Well, in this case, the independent variable is x, right? And b and a are just numbers. Okay, so it's important to remember that sometimes when we write letters, we're referring to a specific number, and sometimes when we write letters like x, we're referring to a value which can change, okay? In this case, we plug in two different numbers for x, 3 and 0, right? But b and a are specific numbers which are already determined by the problem, okay? They're just the names that I give for these two numbers. So those are values, which is a bit of a difference from a variable, right? So in this case, we have a variable x, which is our independent variable, right? We know it's the independent variable because it's inside the parentheses, right? So that's how we can tell what the independent variable here is. If you look at the axis, you can see that we're graphing y here. So I guess you could intuit that y is our dependent variable. Good question. Any other questions? All right, let's move on then. So problem number 2 is pretty similar, okay? All we have to do is interpret these as the average rate of change of g of x over some interval, okay? So now we're kind of going in the reverse. They're giving us f of b minus f of a over b minus a, and we're supposed to say that this represents the average rate of change of g of x on an interval. So we're supposed to tell them what the interval is, I guess. So what is this first one? This is the average rate of change of g of x on what interval? Something comma something else. Well, what do we think? The left one should probably be the smaller number, right? We got two numbers here, 0 and -2. Which one's smaller? -2, right, is smaller than 0. By smaller, I guess I mean less than, not necessarily smaller in magnitude. So we're going to go from -2 to 0. Okay? So remember, it's f of b minus f of a over b minus a. So if you see a b in the b spot, which is 0, that's where I'm going to put it here, because this should be the interval from a to b. Okay? And I use the formula that this is f of b minus f of a over b minus a, okay? So that's how I see that there's a 0 in the b spot, and I see there's a -2 in the a spot. So I just put those into my interval. Okay, so what does it look like on the graph? Well, on the graph, it looks like the slope of a line, our interval, okay, our interval lies right here. So the slope of the line, it should be the slope of the line that goes through the points on the function, on the endpoints of that interval. So it's the slope of this line right here. All right? So let's do one more. I'll do it in blue. This time we go from -4 to 0, right? So this is going to be the average rate of change. I just go look back at my formula. It says the average rate of change of f of x on AB is given by this function, this formula. So I get the formula, and I'm supposed to say that this is the average rate of change over some interval. So all I need to do really is figure out what A and B are. So this is average rate of change of g of x on the interval. Someone shout it out. What's my interval going to be? Yeah, -4, 0 in this case. Great work. All right, so if we go from -4 to 0, what does that look like? That looks like this line here. Okay, so the slope of that line is going to be the average rate of change of this function over that interval. That's because sometimes it's going down, but then there are other spots where it's going up, which completely compensate for that. So the average rate of change is basically like, I didn't do anything, right? It all balances out over the course of this interval. Okay, any questions about that one? Okay, yeah.
Okay, just back to the first one, when you had -2 and 0,
Mhm.
how come for that one it wasn't the same as just a straight line for like the second example, or third?
You mean why wasn't the line horizontal, or?
Correct. Why was it horizontal for the one we just did, but not the first one?
Okay, so it just has to do with our interval. So the a comma b is describing the x values over which we are considering this function changing. So what we want to do is, for our first interval, it just went from -2 to 0. So we want to understand, well, how does the function change between x values -2 and x value 0? So what we want to understand is, how is the function changing on average from here to here? And if you think about it, like, if you made a simplification of what's happening here, you would say, well, it's going up, right? So, yeah, go ahead.
Is it because, like, it doesn't hit anywhere, like on the -4, like going down? You know what I'm saying?
It's more about where it starts and where it ends, okay? So, in this case, we're talking about the average rate of change of the height of the function, okay? So if my height starts at 0, and then it goes down for a while, and then it goes up for a while, and I end up back at 0, then my height from start to finish didn't change. So the average rate of change is 0. Now my height actually did change during that time. It went down and then it went up. It just happened to be that those two processes canceled one another out. So in this case, we get a horizontal line, so the average rate of change is 0, i.e. the height of the function didn't change from -4 to 0. I mean, it did change, but on average, the end result is that it stayed the same from end to end. Does that clear up some of the confusion? All right. If you have more questions about this, let's talk after class or in office hours. All right, problem 3 you can do at home, but I'd like to get into groups for this synthesis problem. We'll give it a shot as a group here, and then we'll move on maybe to some other stuff. So get into your groups and give this one a shot together and come to some sort of consensus. Yeah, go ahead. 52 weeks in a year.
Yeah, I didn't give that, but it's asking me for
Oh, I didn't even read the question. I thought you were
Yep. You could use a calculator if you want to, I mean, divide 1450 by 52, yeah, sure. Or you can just leave it as an improper fraction, that's also fine. On an exam or a quiz, I'll always give you math that you can do without a calculator. Okay, I'm seeing most groups are about to finish. Does anybody want a little more time to finish up? Okay, let's talk it over then. So, we're going to try to relate this all the way back to our average rate of change in a minute. But let's first just answer these two questions, okay? So, if we spend in a full year $1,450 on gas, we want to know how much on average do we spend each week. Keyword being on average, right? All right, so what do we think? What should we do here? Yeah, we just divide the total expenditure by the number of weeks, right? Simple enough. Okay, so what do we get? Someone tell me what that is. $27.88. Okay, $27.88. So, question for the class. Does Mary spend $27.88 on gas every week? No, right? Sometimes more, sometimes less. Okay, but this is just going to describe on average how much is she spending on gas each week, right? So if I had a graph and I wanted to understand what this means in terms of the graph, I would think about it in the following way. If C of T is the cost of, total expenditure. Why don't we do E of T? Total expenditure, E of T, okay, is graphed here. So here's our total expenses, and here's our time, right? Then what is the graph going to look like? the graph is going to look like the following. At the end, we hit 1450. So we know that at 52, we're going to hit 1450. But in the middle, some other things might be happening. So maybe the first couple weeks we spend pretty regularly, and then we don't drive our car for like 3 weeks or something like that. And then it goes up some more, okay? And then, I don't know, we don't drive our car for a while, and then Mary goes on a road trip and she spends a lot on gas in like a single week, right? And then not too much the week after, right? So this might be what our total expenditure looks like, right? So who can tell me what $27.88 means geometrically in terms of this graph? What does it describe geometrically speaking? Yeah, Jack?
It would be the slope if you had gone directly from 0 to 1450.
Exactly. It would be the slope of this line, which goes directly from 0, 0 to 52, 1450, which is to say the following. Okay, Mary has very erratic spending on gas, right? But if her friend Sarah has like an amazing routine and does the exact same thing every single week and drives the exact same amount of miles every single week and spends money at the gas station just enough to keep her car going, this is what that would look like, okay? Which is to say that in the end, the result is the same. They both spend $1,450 on gas during that year, right? But it's a very different kind of way of getting to that point, right? Okay, so this is just another basic idea behind the average rate of change. Okay, so if nothing major changes, how much should Mary budget for gas for the next 3 weeks? What do we think? $83.64. How'd you come to that figure?
Multiply the average rate of change being 27.88 by 3.
Yeah, so we multiply the average rate of change, so the average expenditure. We think that we spend approximately this much money per week, and we're going to spend that much money times 3 weeks, and we get, what is it, 83.64. Okay. So this is not a guarantee to cover all of Mary's gas, but if Mary knows that the next 3 weeks are going to be pretty average in terms of gas expenditure, then this is how much she might want to budget. Okay. What do we think about that problem? Easy, hard? Let's give some thumbs. Thumbs up if you feel like, I'm okay with that. Thumbs down if you're like, that's not so okay with me. And somewhere in the middle if you're somewhere in the middle. Okay. Okay. It's looking fairly okay. If you have some more questions about it, then stay after class and we'll chat. Okay. Average velocity. Well, how do we do average velocity? Well, velocity is nothing but a rate of change of a special type of function, right? Okay, so v of t is the rate of change of a distance function, right? Okay, velocity is a rate of change of a distance function. So, between time 1, parentheses t1, and time 2, parentheses t2, the average velocity is given by, well, if the velocity is the rate of change of the distance function, and I want to find the average velocity, then what I should do is find the, so if I put an average here, I should put an average here, right? And do the average velocity will be the average rate of change of d of t. So in this particular circumstance, we just need to find d of t1 minus d of t, sorry, I should do d of t2, excuse me, d of t2 minus d of t1 divided by t2 minus t1, okay? So just a reminder here, these functions are functions of a variable t, okay? So t is a variable, but when I write something like t1 and t2, I'm talking about specific times, specific numbers, okay? All right, any questions on that one? Yeah, Ryan.
Can you do like the change in D or the change in T to find that? Or is that the same thing?
Right, exactly. So this is basically, if you think about the difference between two distances, what you're going to get is a measurement of length or distance. And if you take a difference in times, you're going to get a measurement in terms of an amount of time, right? And if you take a distance and you divide it by a time, you're going to get a velocity, right? But what's different about this is to say the following. If I have like a velocity function, not a velocity function, if I have a distance function, which looks like this, right? What does it say really? It says, well, I'm going away from something, right? So my distance away from something is growing. But it's growing faster and faster, right? Which means that my velocity is increasing, which means that my acceleration is positive, right? So if you look at just t2 and t1, and you look at what is d of t2 minus d of d1 over t2 minus t1, well, that's the slope of the direct path, right? That's the slope of the direct path. So it's to say, well, if instead of driving slowly and then accelerating and accelerating, if I just drove at a constant speed the whole time, if I drove at this particular speed, then I would arrive at the same location in the same amount of time. Okay, am I getting like way too into this example now? Okay, is this okay with everyone? Any other questions? Okay, so that's average velocity. All right, let's see an example of how we would actually apply that. Well, all it really is a specific example of average rate of change, right? It's just average rate of change of a specific function that happens to be the distance function. So here we have a table with function values for distance, and we're supposed to find out what is Jacob's average velocity between the start of the trip and 3 minutes in. Well, for the first minute, Jacob goes really fast. He goes 2,200 feet. And the next minute, he slows down a lot, right? So it's like, 2,200. And then this one is like plus 400. And then this one is plus 600. Okay? So what we want to know is how fast would Jacob need to be moving if he moved at a constant velocity for those first 3 minutes, such that he would still get to 3,300 feet in 3 minutes. Okay, that's our question. So in the end, all we're going to do is apply the formula. And in this case, we're talking about start of the trip. That means T1 is equal to 0, and 3 minutes in, which means that T2 is equal to 3, right? So in this case, we're just going to do d of T2, that's 3, minus d of T1, that's 0, over 3 minus 0. It's that easy. Okay? So in this case, if we take 3 as our time and we plug it into the distance function, then we get 3,300, okay? So I'm going to write 3,300 minus 0 divided by 3 minus 0, which is 1,100. And I guess the units in this circumstance are feet per minute. okay? Feet per minute. Okay, so one more time with the graph. What does the graph of this thing look like? If this is our distance function, well, we go all the way up to 2200, and then to 2600, and then to 3300, right? But in terms of the graph, it looks like this, that this is 1, 2, and 3 minutes in. For the first minute, Jacob goes really fast. And then for the second minute, it's slow. And then for the third minute, it's, I guess, slightly faster than that, right? So this is what the distance function looks like. But it's to say that if I just walked or drove or whatever he's doing, I guess he's walking or running or something. Anyway, he's on foot. If I just ran or jogged at a constant speed, instead of doing what Jacob did, which was sprint for a while and then slowly walk and then walk slightly faster, if I just jogged at a constant speed, I would make it to the same place in the same amount of time. Okay, so this is the idea behind average velocity. Okay, any questions on that one? All right, you can do t2 and t equals 3 at home if you want. All right, one more thing to talk about in this section. I know I'm doing a lot of talking, but we're a little behind. I'm trying to get caught up here. Okay, so relative change. So everybody shops for clothes, right? Everyone has shopped for clothes at some point. And I always get confused when I go into the store and everything's marked as like 70% off. But I see the tag and I feel like if it was really $70, would they really sell it to me for like $20? That makes no sense to me. But anyway, so when we have a sale price, okay, they always tell us something is like 70% off or something has undergone a 33% reduction, right? Like we'd love to know that there'd be like a 33% reduction in COVID cases or something like that, right? So this is how we do the math vis-a-vis relative change. Okay, so we start with our initial quantity. So Q0 is going to be our original quantity. Original quantity. Or in other words, if you're shopping for clothes, that's the list price. Okay, the original price. And then we have Q1, which is our new quantity. Or the sale price, right? Okay, so the relative change from Q0, that's Q0, to Q1. Okay, so from the list price to the sales price is given by this formula. We take Q1 minus Q0 and we divide it by Q0, which could also be written as the change in Q, okay, delta Q, over Q0. Okay, so pretty standard stuff. The only thing that I find students find tricky to remember is that Q0 is what goes on the bottom. So sometimes people think, well, am I supposed to put Q0 or Q1 on the bottom? Usually people know that on the top you got to subtract the two prices, right? But in terms of which one is your reference point, the reference point is always the starting value, okay? It's always the starting value. Okay, so let's see an example. I think this one's an example of an increase. So in January 2017, Tom had 1.5 million YouTube subscribers. I wish I had 1.5 million YouTube subscribers. Today, the channel has 2 million. Okay, so all we need to think about is, well, what is our Q0? What is our Q1? And then what is Q1 minus Q0 over Q0, right? So Q0 is always our original quantity. So in this circumstance, the original quantity is how many subscribers I had before, right? So Q0 is going to be our 1.5 million. Oops, 1.5 mil. And our Q1 is going to be 2 million. Okay, so what do we get if we plug in? Well, all we're going to do is 2 minus 1.5 over 1.5, right? So we get 0.5 over 1.5, which in this case is 1/3? So 33% increase. Okay. So fairly standard stuff, it's just plugging into the formula. But the tricky thing to remember is that the number which goes on the bottom of our fraction is always the original quantity. Okay? All right, any questions about relative change?
Yeah, so is relative change similar or the same as percent change but in a different form?
Yeah, percent change is it's not a different form, they're synonyms. Yeah. Percent change, exactly. But the percent should always refer back to the original quantity, okay, not to the new quantity. Any other questions on relative change? All right. Then, all right, let's do one more example here. Okay, we'll do this one together. So Sam's girlfriend's puppy is back. Was originally priced at $980. Okay, but he got the puppy on sale for $650. So we want to know how much of a sale did Sam get? Okay, so this is a classic example of a relative change problem. They don't put relative change in the problem, but you see these keywords here, how much of a sale. They're asking for like a percentage here, right? What's the percent off? Okay, so in this circumstance, what's our Q not going to be? 650 or 980? I'm hearing both. 980, okay. 980, right? Because Q naught should be, another way to think about it is, this naught here, you can think of it also as an O, as in O for original, right? So original price, well, we read here, originally priced 980, so that's how we get Q naught. And then Q1 is just the other one, right? 650. Okay, so let's do this one. 980 minus 650 divided by 650. Done? Are we happy with that? Why are we not happy with that? That's right, exactly. I tried to trick you all, okay? But this is an easy mistake that you could make on a quiz or a test, is you just say, oh yeah, just subtract those two numbers and then put the other number on the bottom, done, right? But we gotta remember the number which we should be referencing for the denominator should be the original price, okay? So I put Q1 here to try to trick you all, but it didn't work.
Wait, is the formula Q1 minus Q naught or the opposite?
Oh yeah, excuse me. It should be 650 minus 900 as well. I didn't even catch that mistake. Very good. So Q1 minus Q naught. Okay, we do 650 minus 980, and we divide by the original price, which is 980. Okay, so yeah, you're going to get a negative number here, which makes sense because it's a sale price, right? Okay, so that's how we do that one. Any questions on this one? All right. Man, I am going so slowly, I feel like. Or I feel like maybe I just budgeted way too much material for this amount of time. Oh well, we'll get through it eventually. All right, last topic for this section is concavity. And I'm always really confused about why concavity is taught in this section, because it's not taught in a mathematically rigorous way. But I'm going to teach you how to identify it by eye. Okay? So we have two basic properties of a function. So a function can be one of two properties. Can be concave up or concave down, or neither. Okay, and I'm going to teach you how to identify this by looking at the graph of a function. So by looking at the graph, if if the graph is bending upward, so what does that look like? Kind of like this, I guess. Then it is concave up. And likewise, if the graph is bending downward, like so, then it is concave down. Okay. So what is this really describing? It's not describing whether the function is going up or going down. It's describing the shape of the curvature, okay? So you might have, for example, on your car, a convex mirror, right? It's one of those mirrors that bends outwards, right? And that allows you to see more things in the mirror, right? Or if you do makeup, you might have a concave mirror. It's always really weird because it like flips you upside down if you're far enough away or something. So this is the idea behind concavity. It's about the shape of the curvature, okay? So if the curvature is shaping upwards, okay, then it's concave up. And if the curvature is shaping downwards, then it's concave down. Later, we'll have a much more precise way of actually defining concavity. One other useful trick that some people like is to think about it in the following way. If you think about this as being in a car, okay? If I'm in a car and I'm following this path, okay? So this is the front of the car. Then you can think about, well, if I was following such a path, which way would I be turning the steering wheel? Okay, that's another way to think about concavity. So if I'm following this path here, I'd be turning my steering wheel to the left, right, for this whole path. And on this one, I'd be turning my steering wheel right to the right, if I was following that path from a bird's eye view, right? So that's another way you can think about concavity. Okay, any other questions on concavity? Yeah.
So will functions that are concave on a graph, will they always have that bent shape, or I guess the curved shape, or can it be slightly less of a concave line, but still be concave, if that makes sense?
Well, yeah, I guess I didn't describe the last case, which is neither, right? So if we think about concave up as being turning the steering wheel to the left and concave down as being turning the steering wheel to the right, what do we think neither is?
Straight.
Yeah, going straight, which would look like a line. Okay, so a line has no concavity. Does that answer your question?
Yeah, but an exponential. that
Well,
would have
an exponential function looks like this, right? So what do you think, concave up or down?
Upwards.
Yeah, up. it's bending upwards. We'd be turning the steering wheel to the left. Okay, so one last thing that I'd like to give for concavity is a table here. Okay, I like to give the table in the following way. Okay, I do increasing and decreasing and concave up versus concave down. Okay, so what does it look like if we have a function which is simultaneously increasing and concave up? It looks like this, right? Maybe I can get it more curved. Looks like that. Okay, and if it's concave up and decreasing, then we're still turning the steering wheel to the left, but we're going down. Okay, so that's what it would look like. And if we're concave down and increasing, that means we're going up, but we're bending downwards. So that would look like this. And then if we're concave down and decreasing, then we're going down and we're bending down. So it would look like this. Okay, so that's a useful table to refer back to when you want to identify concavity versus increasing and decreasing. Okay, one last tip for concave up and concave down is to remember that the words have a clue. If you think about it, concave up, in the words concave up, the letter U is concave up. And in the words concave down, then the letter N is concave down. That's another good mnemonic device for remembering concavity. Okay, but it's really describing this kind of ethereal property of what is the shape of this function? How is it bending? Any questions on concavity? All right, let's do this next one together. We're not going to do it as a group. All right, so we want to find pairs of consecutive points which are concave up, concave down, concave up, concave down, and either decreasing or increasing. Okay, so let's just classify each section from front to back. From A to B, what do we think? Are we increasing or decreasing? Increasing. And are we bending downwards or upwards?
Upwards.
I know it seems like we're going up here, which is why concavity is so confusing before we really quantify it properly. But we're bending to the right, which eventually would send us downwards. Okay, so in this circumstance, we're increasing, but we're bending downwards. So this is concave down. If you think about it, this looks like it could be a part of the letter N, but it couldn't be a part of the letter U, right? See what I mean? So in this case, I think A to B is increasing and concave down. So that's A to B. All right, how about B to C? Increasing or decreasing? Decreasing. And has our bending changed? No, our bending is the same. So we're still bending down, but we're decreasing. So B to C, we are decreasing and concave down. All right, how about C to D? Has anything changed? Yes, what has changed? Yeah, the concavity has changed. We're still going down, but the bending has changed. Here we were bending downwards and going down, but here we're going down, but the way that our steering wheel should be aligned has changed. Here we were turning it to the right, and now we're turning it to the left. Okay, so the concavity has switched. So C to D, we are still, what am I doing? These should be switched, right? Yeah. Okay, yeah, if I make a mistake like that, just yell at me. Okay, so those should be switched, and then the next one, C to D is concave up and decreasing. C to D. Okay. You do the rest. Okay, another thing you can do is just take this table, right, and just check, well, which of these pieces look like this? This one kind of looks like that. This one, no, no, no. This one, yes, right? So you can just take those pieces like that and check. That's why I do that table. All right, I think I've beaten that into the ground. Any final questions on concavity? For now, we're just identifying it visually. We happy? All right, let's see, what time is it? I got 9 minutes left. I am gonna try to start the next section. Okay, so there's a warm-up problem which you can do at home. Okay, but I want to give you the proper book definitions for these functions. Okay, so the cost function and the revenue function and the profit function are going to be functions which we're using all the time in this class, especially since it's a business calculus course. Okay, so I told you that calculus is about studying the ways that things change, right? And our costs and our revenue and our profit are quantifiable things which are going to change, which we want to change in certain ways, and we want to understand how they're changing. So the cost function is going to be given by C of Q, okay? The cost function C of Q gives the total cost of producing Q items for sale. Okay? Not necessarily physical items. It could be like, I don't know, Q oil changes or something like that, or services is also fine. Okay, but Q is a quantity of something being sold. Okay? And C is the cost to the producer to produce those items. Okay? Then revenue, okay, R of Q is going to be similar, except it's going to give the total, how do we want to describe this? The total dollar amount I want to be careful about the language here. It's not the dollar amount that we make, the dollar amount for which Q items may be sold. That's how we should put it, may be sold. Okay, so the cost function is the amount of money that me as the producer who wants to sell these items, it costs me C of Q dollars in order for me to produce Q items for sale, right? And then the revenue is the total dollar amount that I would charge my customers in order to buy Q of my item, right? So there's a big difference between revenue and profit. Does anybody know already what the difference between revenue and profit is that can describe it lucidly? What is the difference between revenue and profit? Yeah?
Isn't revenue all just your sales that you've made versus profit is your sales minus your expenses?
Exactly. Okay, the revenue, I said, is the dollar amount for which I can sell Q items. That's not my profit. My profit is the amount of money which I made, which we consider to be the amount of money which we made from selling the items minus the amount of cost that it incurred for me to produce those items. Okay, so that's the difference between cost and revenue. And we use a weird letter for the profit function. Okay, we use the Greek letter pi. Okay, we use pi of Q is equal to our revenue minus our costs. gives the net profit. Okay. Any questions so far? Okay, a couple more definitions here. Marginal profit, revenue, cost is the rate of change of the cost. Why don't I say profit? Why don't I say rate of change of pi of q, r of q, and c of q respectively. Okay, so the marginal profit is the rate at which the profit is changing. Okay? If our profit function is linear, then that means it's the slope of the profit function, or the slope of the revenue function, or the slope of the cost function. Okay, if they're linear. Which, spoiler alert, most of the time they won't be in this class, and they'll almost never be in real life either. Okay, so another way you can think about marginal profit is marginal profit at Q units is the profit gained from selling the Q plus 1st, Q plus 1st, Q plus 1th, I don't know, why don't we do Q plus 1th with a TH? Q plus 1th item. Okay? So if our profit function looks all wiggly, okay, then if we're at Q to Q plus 1, we just look at what is the amount which our money is going to go up based on this 1 unit increase. Okay? This is how we can think about marginal profit and marginal revenue and marginal cost in a looser sense. Okay, I think we can close there for today. Thanks for your attention. I'll see you on Tuesday. Don't forget the homework is due on Tuesday, by the way. Which I guess I'll have to extend the deadline. So never mind, I'll extend the deadline for the homework.
Schedule like a time to meet with you. I have a class right after this, so I can't do the like.
Yeah, sure. You have a specific thing that you want to meet about right now, or you just asking in general? Okay. How about Thursday before class? Can you come then?
I have a class right before this one too.
Okay, so not Thursday before class. How
Tuesday
about...
and Thursday's been crazy.
Okay, then we could... I would say just send me an email and say, if you have a concern about something, then send me an email and say, hey, I'd like to meet with you. I'm free during these times on, whatever, Monday, Wednesday, Friday. If you're free on those days, just send me an email saying, this is my availability. I'd like to meet with you for this purpose. And then do it that way. Does that work?
Okay, yeah, that works. All right, thank
Okay.
you.
Yeah, sure thing.
I'm just telling them about my readiness test. I was taking it last night, and it pretty much just like, I'll show you what it looks like now, but I tried to get back into it. And I was done too, but I'm happy to retake it if I need.
Brian, here is your quiz. Let me go ahead and give that a shot. Okay, so what happened with it? You just
I'll
it
show you.
kicked you out.
Yeah. Sorry, I'm on Wi-Fi right now. Give me 1 second.